So, let us have a quick recap on what we have done so far. We defined magnetic field from the force equation Q V cross B. Then we showed that this magnetic field is a requirement of special theory of relativity. If Lorentz transformation works, if that length contraction works, then as you change from one frame to other frame, what is a pure electric field in one frame becomes a combination of electric and magnetic field in the other. So, this kind of transformation we have dealt in detail during our course on special theory of relativity, but nevertheless this is interesting to note that this electric field and magnetic field, they are not two separate entities as such. If you are in a particular inertial frame, yes, these are two separate entities, they behave in different manners, but in principle it is one entity electromagnetic field, and these are only two phases, and the phases can change once you change your inertial frame. So, that we discussed. Then we talked about the effect of magnetic field on charged particles and current elements. Then we showed the motion of charged particle in a uniform magnetic field, in a non-uniform magnetic field, in combination of electric and magnetic field. Then we talked torques on the current loops and all those things. So, today we will be starting a new chapter, and that is how these currents are produced from the current. What is the rule, what is the equation, how do I find the magnitude and direction of magnetic field if the current distribution is given. So, at +2 level, you know that the current is produced by the motion of charges, and then the moving charges or the currents, they produce magnetic field, and the basic equation for calculating this magnetic field from the current element is called Bio and Savart law. And you know this, if you have a current element, take a current element, I will talk what is this current element, and then you have some point P where you want magnetic field due to this current element, then you connect this current element to this point P, call this vector position vector r of the point where field is needed, and starting from the current element because of which the field is needed, and then you say that the magnetic field at this point due to this current element is mu naught by 4 pi, then I dl vector cross r vector and divided by r cube. That is what we understand from this Biot-Savart law. It gives me the magnetic field at a point P because of this current element and given by this. This you have all done very well. And the important thing is that this current element is not a stand alone current. It cannot be. The current cannot just keep going from here to here and nothing else in the world. It is part of a circuit. Current is always in a circuit. So, it is part of the circuit, and from this part this much is the magnetic field. The field here due to the entire circuit is to be obtained by properly integrating this equation. This mu naught also, you know, it is 4 pi times 10 to the power minus 7, and that is in SI units, and what the units are that you can just work out from here. This side is Tesla and this is mu naught by 4 pi, we do not need. Then I is the current which will be in ampere, and then length, length and length cube. So, it is 1 by length, dl is a length, r is a length, r cube is cube of the length. So, it is 1 by length. So, 1 by length. So, this mu naught, the unit will be Tesla meter per ampere, Tesla meter per ampere. You do not have to remember, I do not remember all the time what is the SI unit. Whenever need arises, I can just derive this way. This is Tesla, this is mu naught, 4 pi is a number, I is current in ampere, then this is length, length square, and this is length cube. So, it is 1 by length. So, it is 1 by length is meter. So, mu naught will be Tesla meter divided by ampere. So, this is a universal constant, by definition it is this. So, you have already studied in high schools how to calculate the first example or first application of Matt-Seward law is perhaps you have a long straight wire carrying a current I, and you need magnetic field at some distance, given distance from the this current. So, you have a current, you have a long straight wire and it carries a current, and then a point P is given, and the distance of this point P, perpendicular distance, is let us say r, and then you take this ideal cross r, etc., integrate this and get the result B. At this point is mu naught over 4 pi, then the current I here and this r here. In which direction? In which direction? That is given by the right hand thumb rule. Your thumb should be along the current, and then the curling finger gives you the direction of the magnetic field there. I will rederive it, but with cylindrical polar coordinates, so that you get a practice of using cylindrical polar coordinates also. So, remember, cylindrical polar coordinate, we take an origin, since this is a given point and this is a given line. So, I can put the origin at the foot of perpendicular here O, this is taken as the z axis. So, this is our z axis. The coordinates of any points are given in terms of s, phi and z. S is the axial distance of the given point. If I take this point P, then this r, this is our s coordinate. Perpendicular distance from the z axis is the s coordinate, and the direction, unit vector in direction of that perpendicular, that is s vector. So, this will be our s vector here. Wherever this point you take, you will have a different s vector. Drop a perpendicular from the point and then extend it on the other side, and that is s cap direction. Z cap direction is simple to understand. This is our z cap direction, and then the phi cap direction is obtained by those cross product relations. S cap cross phi cap will be equal to z cap, and so on. Phi cap cross z cap will be equal to s cap, and so on, like that. S, phi and z, z cap cross s cap, z cap cross s cap will be phi cap. So, if this is s and this is z, z cross s is phi, this is z, this is s. If you do this cross product z cap to s cap, it will be going into the board. So, your phi cap direction is going into the board, inside the board, perpendicular to this, inside the board. So, these are the unit vectors here. Now, to get the magnetic field, because of this long current, and what is the meaning of this long current? Can you have a long wire? and then just pass current into that. You have to have a circuit, a loop. So, if you have a circuit, a loop, you have inside batteries and all those things, some current is going. The current always has to go in a loop. In that case, if you take a point P, let us say here, somewhere here, and ask the magnetic field due to this whole circuit, these points, these points, these points, these points, these points are far away, these points are far away. They are giving only a negligible contribution to the magnetic field here. The contribution mainly comes from these points because they are close, and let us say up to here. You have significant contribution. Of course, the contributions will be there from everywhere, but significant contribution comes from, say, this part, and this is long as compared to this separation. Okay, so typically if your circuit is, let us say, a few centimeters, 15 centimeters, 10 centimeters, like that, and this is, say, 3-4 millimeters, then yes, that the fit case, or you can always neglect all these things. These things also you can neglect, and therefore the contribution comes from here, nothing here, to extend it mentally. If there was a current from here to here, that will produce the same magnetic, almost same magnetic field as this part is producing. So, getting the actual magnetic field in a circuit close to the wire, this formula will be applicable. So, that is the significance of this. So, let us start working. dB. dB is mu naught 4 pi I r cube dl cross r. What is this dl vector? What is this dl vector? So, you take an element, and how do we take an element? At some, if it is on this z axis, you go to that z here, z distance here, and then take this dz. dz is always increment in z. So, this is our dz, this will be our dl. So, dl will be dz k cap. K cap or z cap, same thing. In the z direction, the unit vector is written as z cap, it is also written as k cap. So, this dl is this. What is this r? What is this r vector? This is the vector from the current elements to the point where the field is needed. So, here is the current element, here is the point. So, this is our r vector. This is our r vector. This r vector you can write as, let me give some names, let us call it p, q, we have already r we have used here. Okay. So, small abc, let us call this point as a, small a, this point is already p here, okay, this is already p here, then let us call it d here, and this is of course o. So, r vector is this dp vector, and dp vector you can write as do vector plus op vector, right. This dp vector you can write as do vector plus op vector, and this dp vector is this do vector, do, this is minus zk cap, right, d to o, this is minus, z is the magnitude, it is in downward direction. So, minus z k cap and plus op. What is this op? This op is r, this op is r, the distance from the wire here, and in which direction is op? op is in the direction of s cap. So, it is s cap. So, that is r vector. Now, calculate dB. dB vector mu naught I by 4 pi, mu naught I by 4 pi. Then dl vector cross r vector. Here is dl vector and here is r vector. So dz k cap cross minus z k cap is 0. K cap cross k cap is 0. So you are left with this term. This is r into dz k cap cross s cap. R into dz, r into dz, r into dz, and k cap cross s cap, k cap cross s cap is phi cap. So this is r dz phi cap. So that is the numerator, and denominator is r cube. R is this position vector and its own magnitude is this z square plus this capital R square. So it is z square capital R square and square root of that. That is the magnitude of this, and then you have to put a 3 power 3. So this will be 3 by 2. This is the magnetic field. Due to this current element here at this point P, we need magnetic field due to all these currents elements taken together, the whole current in this long wire. So we have to integrate, but be careful if it is Cartesian coordinates, and if you have I cap here or j cap here or k cap here, no problem. But in cylindrical coordinate, this s cap and phi cap, k cap is fine, but s cap and phi cap, they can change their directions depending on which point you are working at. And if this vector can change its direction, then you cannot just integrate this other part and then put this phi cap. You cannot take phi cap out of the integration sign if it changes from one place to the other place. But in our case here, when I am integrating, I am varying this dz. When I am integrating, I am varying this z. I am taking the element here, I am taking the element here, I am taking the element here, I am taking the element here. So that is how we have to sum, we have to add, we have to integrate. Now independent of whether my dz is here or dz is here or dz is here, this s cap, phi cap, z cap, this direction is not changing. S comma phi comma z is the coordinate of this point P. This point P is fixed. I am changing z. I am here, I am here, I am here, I am here, I am. I want to write magnetic field from this element, this element, this element, this element. I am changing those things, but the point P is fixed, origin is fixed, z axis is fixed, and therefore s cap is fixed, z cap is fixed, phi cap is fixed. For this integration, this particular example, this phi cap is not changing during the integration, and therefore I can write this b, as integration of this mu naught I by 4 pi, this also we will take out, r capital Z, r and dz here, and then z square plus r square 3 by 2 here, and phi cap here. This integration we can write as mu naught, I can take out this current I can take out, this capital R I can take out, this 4 pi I can take out, and this phi cap also I can take out. So it will be integration of dz, and then here z square plus r square, and then 3 by 2. bracket closed and phi cap. We can do that. We can do that. Now it's a simple calculus exercise. We have to integrate dz z square plus r square 3 by 2 and limit z. What is z? At z we are taking this element dz. So if I have to start from here and go up to here, we can put that limit minus infinity to plus infinity. So this is what we have to do, z from minus infinity to plus infinity. The procedure is very simple for this type. You write z is equal to r tan theta, substitution. You write z is equal to r tan theta, and here fortunately this theta, we know from this figure what is that angle theta. Even if I do not know, I can integrate just by substituting, changing the variable. Tan theta is z by r, this is z, this is r. So this angle is theta, this angle is theta. And if I write dz, this will be r sec square theta d theta, and z square plus r square. Z square plus r square is z square is r square tan square theta, and plus r square, this is r square taken common, 1 plus tan square theta, and that is r square and sec square theta. That is our z square plus r square to the power 3 by 2, to the power 3 by 2, z square plus r square to the power 3 by 2. So to the power 3 by 2 will be r cube sec cube theta. Put everything here and see what happens. Dz is r sec square theta d theta. So r sec square theta and d theta. Dz is r sec square theta d theta. Z square plus r square 3 by 2 is r cube, capital R cube, and then sec cube theta. So it is sec cube theta, and that is 1 by r square. So r square goes here, sec square here, sec cube here. So you get sec here, which will be cos theta. So this is cos theta, and this is d theta, and that is sine of theta. Integration of cos theta d theta is sine theta. This r square is constant. You can take out 1 by capital R square. You have to put proper limits. You have to put proper limits. What are the limits? What are the limits on theta? We know the limits on z. So it's easier to find the corresponding limits of theta from here and put it there directly. So if z is minus infinity and then z becomes plus infinity. So at minus infinity, what happens? If this is minus infinity, tan theta is minus infinity. So theta is minus pi by 2. So you put minus pi by 2 here. And similarly, z becomes plus infinity. I go up on the wire. So z is plus infinity, and divided by r is of course finite. So tan theta is positive infinity, that is pi by 2. So this is pi by 2. Sine of pi by 2 is 1, sine of minus pi by 2 is minus 1, and then you have another minus in between. So this will become 2. So this is 2 by r square. This is 2 by r square. 2 by r square. Remember, this integration is 2 by capital R square. So we put those values. So I will erase this. I will erase this. Make a space and then write B is equal to. This B is equal to mu naught I capital R 4 pi, then this integration, and this integration is 2 by r square, 2 by r square, 1 by r square is here, and then this 1 here and minus 1 here, so that is 2 by r square, so 2 by r square, and this phi cap, this is equal to mu naught I, 2 here, 4 pi here, so 2 pi here, r square here, so r here, phi cap. Okay, so this exercise I had done you to get familiar with cylindrical coordinates, very useful coordinate system for practical purposes. When many of the problems you will encounter such situations that cylindrical coordinate system will be much easier to work with as compared to the Cartesian coordinates.